Yeah. No. Thank you very much. This is not an official YouTube video. This is only for my students. Thank you. Thank you for watching it. Okay? If at any time you feel like you're missing me, this is when you're going to come back and listen to my videos. Okay, here we go. So the next thing that we're going to do is chapter 8, maybe 9, maybe 10. We'll try to get all of those in, which is sound, waves, and wave interactions. Now, chapter 8 was pretty straightforward when we're looking at sound. Yes, who can remember what some of the important concepts that we looked at? See what? But before that, what are the 3 kinds of waves? Yes. Okay. Okay, so we had 3 kinds of waves. Your transverse waves, longitudinal, and the last one is torsional. So transverse waves, waves, for example, that basically, just like water waves, your motion and the wave height are perpendicular to each other. Okay, longitudinal waves, so example here, water waves. Okay, longitudinal waves are sound waves, where you have areas of compression and rarefaction and compression and rarefaction. So compression, rarefaction. Okay, and the last one is torsional waves, where the object is moving in 2 different patterns. We're moving forward, but they're also turning in a particular way. So example would be a screw, for example. So this is a torsional wave. Now we're going to more concentrate on the transverse and longitudinal waves. Okay. When we talk about waves, one of the first things we look at in terms of waves are some of the parts of the wave. So of course this is known as your crest. And this is your trough. There's your trough right here. Okay? All right. Trough is your bottom. Okay, this is your equilibrium right here. And these right here. So your amplitude. Okay. Another word for the amplitude is the wave height. Okay. And from here to here, this is known as wavelength, lambda, measured in meters. Measured in meters. Is amplitude half of, yes, that's correct, it is. So amplitude is half of wave height. Yeah, absolutely correct. Wave height is the total height of the wave. Amplitude is from the equilibrium. Okay. All right. So these are some of the parts of the waves that we've talked about before. When we are talking about the relationship that these have with each other, all waves are governed by one simple formula. And that formula, of course, is V equals to F times lambda. V, of course, is your velocity in meters per second. F is your frequency, and lambda is your wavelength. Okay. Now, when we're talking about frequency, frequency is how often something is taking place. Can I erase this bottom part? Okay. So now the formulas for frequency are F equals to cycles divided by time, and frequency is measured in hertz. Okay, frequency measured in hertz. Period, the symbol for period is T, which is time divided by cycles, and this is measured in seconds. Okay, so one of the formulas is cycles divided by time, time divided by cycles. Of course, another formula is F equals to 1 over T, and T equals to 1 over F. Okay? Excuse me. What do we do after this? What was the next section that we looked at? We did the V of sound. velocity of sound, which is velocity of sound, of course, is dependent on temperature. So normally in air, the colder the temperature, the lower the velocity of sound. Basically in air, the denser the air, the slower the speed of sound. However, that is not the case for other objects. So, I mean, that's not the case in other states. So, in liquids and solids, general rule is sound is faster in more denser objects or states, objects, like water and steel. Okay? So, in air, density is opposite, the speed of sound is opposite to what it is in other materials. So formula is 331.4 meters per second plus 0.606 times T, and T of course is your temperature. So at 0 degrees Celsius, your velocity of your sound should be 331.4 meters per second. This is the velocity of sound in air. Okay, what else did we do after this? Mach number. So we talked about how we can go faster than the speed of sound when it comes to planes and jet fighters, etc., etc. And Mach number was how fast you are going in terms of the speed of sound at that place. So Mach number is very closely related to breaking the sound barrier, of course. Okay, what was the formula again? Speed of object, divided by local speed of sound. Of course, Mach number does not have any variables. It's just a ratio between one and the other. Okay? What else did we do after this? Okay, so we also talked about when we're talking about okay, so after this was that was the end of chapter 8. There are a few other things. In chapter 9 we started looking at vibrations in strings. Okay, but that's also chapter 9. Yeah, so we started talking about strings and vibrations, and we said when my object interacts, first things, when I send a pulse through a string, for example, that is tied to a pole, then that wave will return back inversely. If it's no pole at the end, so this is known as a fixed end, and this is known as a free end, then this wave will return back in its same non-inverted form. The two waves, one going this way and the wave returning back, interact with each other to create something known as a, what is it known as? A standing wave. Now a standing wave basically literally looks like the wave is standing. In reality it's not, but because the waves are interacting with what kind of interference taking place? Constructive and destructive interference. Okay, interference. Now, wherever constructive interference is taking place, what do we have? What are those known as where constructive interference is taking place? These are known as antinodes. Okay, and basically that's your crest and your crest combining together to give you a supercrest. So crest, supercrest. Okay, wherever your crest and your trough meet, they give you a node. So these are nodes at the end where destructive interference is taking place. Now this is both for strings, open air columns, and closed air columns. Let's see if we can try to fit in all of those in this one video. We'll try our best. Okay, so when we take a string of a particular length and we start sending interference patterns through, That means our pulses are continuously going back and forth. The lowest frequency at which this standing wave pattern is formed is known as a fundamental frequency. Fundamental frequency. Another name for it is the first harmonic. Okay, now if we continue doing this, my wave will continue and will start forming more vibrations. By the way, what is the value of this wavelength right here? How much is it? Half a lambda. So that's half a lambda. This is 1 lambda. Half a lambda plus half a lambda. There is your node, node, and node. This is your antinode and antinode. This is known as the second harmonic and also the first overtone. Overtone basically means one frequency above the fundamental frequency. Okay? All right. If we continue again, you get the picture. My vibrations increase by half a lambda. Okay, so now this is 1.5 lambda. Again, node, 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 and node. This is antinode, antinode, antinode. This is known as the third harmonic and the second overtone. Now there is a relationship between the antinodes, the nodes, and the length of my string. What is that relationship? Who can tell me that? N divided by 2 lambda. Now this is for fixed ends or free ends? This is for fixed ends. So N, of course, stands for your... Okay, so N is antinodes, also known as the harmonics. Okay, L stands for your length in meters. Sorry, this is for a fixed end. Okay, now if I have a free end, can I erase some of this? Yeah. So we're going to talk about open air columns in a few minutes. Okay, so if it's a free end, of course, which means it's not tied down at the end, my formula for L equals to, what is it? N minus 2n minus 1 over 4 times lambda. 2n minus 1 over 4 divided by lambda, or 2n minus 4 divided by, you get the picture. Okay, all right, this is for a free end. Okay, we also had a couple of formulas where we looked at the thickness of a string and the velocity with which my object vibrates. And what are those again? So we talked about, and of course we said that the vibration or the velocity of a string, or the velocity of vibrations in a string, or the velocity of sound in a string is dependent on thickness. What else? Density, tension, and something else. Diameter? I think it was diameter. Can anybody remember what those formulas were? Yeah, what are they? Well, what's the first formula? V equals to something about a square root. Ft divided by mu. And this mu, of course, was the linear density of the string. Okay, so this was, and the formula for mu was m over L. M, of course, is your mass, and L is your length of your string. Okay, so that's one of the first formulas we looked at. The other ones were all, other formulas that we had that looked at thickness, linear density, and all that stuff was frequency 1 divided by frequency 2, which equals to L2 divided by L1, which equals to D2 divided by D1, which equals to F1 divided by F2, which equals to density, D2 divided by D1. Okay, so length, diameter, tension, and density. Wow.